Good morning, I'm Will Yobi, and I'm here to explain how to find a determination of the concentration of a weak acid as we did in experiment number 7. Today I'll be talking about the background of titration, the purpose of the experiment, the results of our experiment, calculations, and the discussion questions at the end. Titration is a scientific method used to find the concentration of an unknown solution while using a concentration of a solution that you already know. This is also performed with a burette into Erlenmeyer flasks, so that way you know what the volume that you put into the solution is. The purpose of our experiment was to calculate the molarity of an unknown acetic acid and then to find the standard deviation of this molarity. For this experiment, first we had to clean up all of the equipment, make sure everything was clean, ready for us to use. And then we had to weigh out 0.3 between and 0.4 grams of the KHP. We added this to 100 milliliters of distilled water and mixed it until the KHP was completely dissolved within the water. Then we added 2 drops of phenolphthalein, which was an indicator to show when the titration was complete. The NaOH was titrated from the burette into the Erlenmeyer flask, and we continued to do this until the end of the experiment when the solution turned pink. This was repeated for all 4 of the solutions, and at the very end of the experiment we cleaned everything up and put it where we found it. To start the equation, you had to make your own balanced equation of the NaOH, and here's a chart of the mass of the KHP for all 4 trials, and the final, initial, and the total volume of the NaOH that was used in each of the trials. We had to find the molarity of the NaOH, and I used trial number 1 to show how to do this. You took the mass of the KHP and divided by the molar mass to find the moles of the KHP. And then you took the moles of the KHP and used your stoichiometric ratio to find the moles of the NaOH. And once we had the moles of the NaOH, you had to divide by the liters of the NaOH added during titration from the burette, and that gave you the molarity of the NaOH. And here's a chart of all the molarities of the NaOH, and I took the 3 closest, and I added those together and divided by 3 to find the average. To find the standard deviation, we took each of the 3 trials that we used for the average and subtracted from the average that we calculated and divided by 2, and that's how I got here. And then once you divide by 2, you took the square root of that to find the actual standard deviation. My unknown acid was number 86, and here's a chart of what we used for each trial for the final initial burette readings and the total volume of the NaOH that was used. To find the molarity of the unknown acid, I used trial 1 again to calculate this, and I used the liters of the OH that we used, and I multiplied by the moles that we found. And once you find the moles of the OH, you can use the stoichiometric ratio to find the moles of the H+. And once you find the moles of the H+, you just divide that by the liters of the unknown acetic acid that we used, which was 10 milliliters, so 0.01 liters. And that gave us the molarity of the unknown acid. And here's a table showing each molarity of the unknown acids. And to find the average of the unknown acids, we took the 3 closest together, added them up, and divided them by 3. To find the standard deviation for this unknown acid, we did the same thing as before. We took the molarity that we found and then subtracted that by the molarity that we averaged out, divided that by 2, and took the square root to find the standard deviation for this molarity. Some of the discussion questions. The first one was, what would happen if your teacher gave you a contaminated substance, NaOH with NaCl? This would cause it to, the molarity of the NaOH to be higher than it should. It would be higher because the actual mass is wrong. So the number on the top of your numerator would be higher than it should be, causing the total number that you found to be higher than it should be. This would also affect the determination of the unknown acid concentration in a very similar way. The numerator would be higher than it should be, and this would cause an inflated numerator and inflated molarity, like if it was 2 divided by 2 equals 1, or 6 divided by 2 equals 3. The 3 is too high because the 6 was too high. The reason we did not weigh out the NaOH was because if we weighed out the KHP, it's better because the NaOH is hygroscopic, and hygroscopic is just when the NaOH absorbs water from the atmosphere. So when we weigh out the NaOH, we're also weighing out H2O from the atmosphere. Even though the weighing out the NaOH would have been quicker, it would have been less accurate compared to weighing out the mass of the KHP. Here is the equation for the sodium carbonate and the HCl. And to find the molarity of the HCl, we took the mass of the sodium carbonate and divided it by the molar mass of the sodium bicarbonate, and that gave us the moles of the sodium carbonate. Once we had the moles of the sodium carbonate, we just had to use the stoichiometric ratio that we found back in this equation for the 2-to-1 ratio, and that gave us the moles of the HCl. Once we had the moles of the HCl, all we had to do was divide by the liters of the HCl, and that gave us the molarity of the HCl that we were trying to look for. And here are my references that I used for this lab. Thank you very much.